For this video, I'm going to focus on Le Chatelier's principle and how these stressors affect an equilibrium. This is usually the section of equilibrium that many people like because it's not too difficult to understand. It's really basically more of an explanation part, not really any math here. So it's really something that you can pretty much take care of. And you usually see questions about this on the AP exam, and they're usually um, home run questions because it's not that difficult of a concept here. So Le Chatelier's principle basically says this: if you apply a stress to a system that's at equilibrium, then the equilibrium will essentially shift in the direction that reduces the stress. This makes complete sense. If you have your equilibrium and you're applying some form of stress to it, it's going to shift in the way to minimize the stress that you just put on it. So there's three stressors that we're going to look at here. We're going to look at concentration. We can change the concentration by either adding a reactant or product, or maybe removing a reactant or removing a product here as it forms, and this will mess with the concentration. We can change the pressure, which would affect an equilibrium here, and we do that by messing with the volume, or we could change the temperature of the system, which would be another stressor here that the equilibrium system would need to respond to. Basically, the rate of the forward or the reverse reaction will change in response to the stressor that we apply. And you can actually predict which way it will change based on the stress that you're applying to a particular system. So that's what we're going to look at here with Le Chatelier's principle. We're going to apply some type of stress, and the equilibrium system is going to respond to wipe out or minimize the stress that was just applied. Let's look at concentration first. If you increase the concentration of a reactant, so think about this, you have more of a reactant, the equilibrium is going to shift the reaction to the right, essentially forming products here in order to use up the added reactants. All right. So then if you increase the concentration of a product, so now if you have too much product, the equilibrium is going to shift to the left to use up the product that you just added to reach that new equilibrium. All right. So it kind of makes sense. If you have more of a reactant, the reaction is going to shift to use up that reactant. If you have more of a product, your reaction is going to shift toward the left side to the forming the reactants to use up that added product. Just be careful here. Whenever you're adding solid or liquid to an equilibrium, they don't participate in the equilibrium expression. All right, so more of a solid or more of a liquid here have no change on the equilibrium itself. So if you have an equilibrium system and there's maybe a solid included in the equation and you add more of that solid, it does nothing to the overall equilibrium because solids and liquids don't participate in the equilibrium. Don't fall for any tricks or traps here. If we look at this picture here, the reaction that's taking place is what's listed here at the bottom. We have N2 plus 3H2 in equilibrium with 2NH3. All right, so what we see here is eventually this system reaches equilibrium and we have these initial concentrations, these initial equilibrium state. Essentially, all three of the concentrations of the substances are the same here over time. So there's no change in the concentration. You're at equilibrium. All right. But then what happens is at this point, we're adding more N2. And you can see that because the concentration of the N2 rapidly increases here. So we've added N2. Well, according to what we just said, if you have more of a reactant, the equilibrium is going to shift to use up that reactant. So it's going to shift to the right and form more products here. And that's exactly what we see happening to the other two substances. If we add N2 right here, notice the concentration of the H2 drops, all right? And that makes sense because if the reaction is going to go forward and form more products, we need the other reactant to be used up. The N2 drops as well because both of the reactants are going to be used up as you're forming more products. And then notice the NH3 actually goes up for its concentration because it shifted to the products here and you're forming more of the products. But notice what happens. Eventually you reach a point where there's no change in the concentrations again, and you have your new equilibrium. So essentially we applied a stress. In this case, we added more of a reactant. The equilibrium shifted to form more products, but eventually you reach that steady concentration for each of the substances again, and a new equilibrium is established. But the system responded to the stress that you put on it in a way that could be predicted. And that's basically Le Chatelier's principle here. If you decrease the concentration of a reactant or product, the reaction is going to shift in the direction that creates more of the substance that was removed. Okay, so if you were to pull out a reactant here, well, now you need to form more of that reactant. So the reaction is going to shift to the left, to the reactant side. If as a product is formed, you start removing that product. Basically, there's not enough product now, so the reaction is going to shift in the direction that forms more of the product. So it would shift to the right here. All right. So again, this is the exact same picture from the previous slide. Again, notice these new equilibrium positions here in the picture. Just like before, messing with a solid or a liquid here, they don't participate in the equilibrium expression. So messing with the solid or liquid has no effect here on the overall equilibrium. Don't fall for any traps. In this picture, we're looking at the exact same reaction that we were looking at before, N2 plus the H2 forming the NH3. So in this case, we have our concentrations here remaining steady for a period of time. So we have our equilibrium established. At this point right here, we're adding hydrogen. All right, hydrogen was a reactant. All right, so if you have more of a reactant, we know the equilibrium is going to shift to use up that reactant and form more product. So we see the reactants, the hydrogen and the nitrogen going down, and the ammonia, the product, going up here, which is what we expect. All right, so then eventually we get the concentrations becoming steady again, and you have your new equilibrium established here. But now at this point, all right, if we add some ammonia, ammonia was a product. So now if you have more product, the equilibrium is going to shift to use up that product, or it's going to shift to the reactant side. So you would expect here to see the reactants going up and the product, the ammonia, going down, which is exactly what we see. All right, so Le Chatelier's principle says when you apply this stress to the system, it's going to shift in a way to minimize that stress, and you can actually predict it. And that's what we're seeing here with the first stressor, concentration. If you remember when we talked about the common ion effect, we said that there's a reduction here in the solubility. Basically, the precipitate is less soluble when you add a compound that has one of the same ions in it. And basically, this is due to Le Chatelier's principle. So now you have another way to think about common ion and another way to explain it. And this should make complete sense here. Essentially, what is happening is we are causing the reaction to shift to the left, to the solid side. Right? That's why there's a reduction here in the solubility. So for example, if we add 0.1 molar NaCl to a solution of AgCl, all right? So think about this here. The solution is AgCl, so the AgCl is our solid, and it's going to be in equilibrium with both of its ions. That's the equilibrium here that we're looking at. By adding NaCl to that, the common ion is Cl minus. We don't care about the Na. It's the Cl minus that's in common here. Essentially, what we just did was we added more of the Cl minus. Well, according to Le Chatelier's principle here, if you have more of a product, the reaction is going to shift in the direction to use up that product. So essentially, we're going to form more of the reactant here. So forming more of the reactant means you're forming more of the solid. Essentially, you are making the substance less soluble. You're going to have less of the ions and more of the solid being undissolved. All right, and that's exactly what common ion tells you. If you have one of the ions here added, you will see a reduction in the solubility because you're essentially causing the reaction to shift to the left, and more of the substance is going to be precipitated out, or essentially less of it will be dissolved. So now you can think about common ion in terms of Le Chatelier's principle here. In general here, if you mix two salt solutions that have a common ion, the salt that has the lower value of the KSP will precipitate first. Assuming that you have the same number of ions for each of these substances, typically these problems require you to show work and to do math. But if you did have a problem, maybe like a multiple choice, where you're trying to figure out, which of these two would precipitate first, you can look at the KSP values here if they have a common ion. And as long as they have the same number of ions, the one that would have the lower value of the KSP would precipitate first. But obviously, if you need to show work, you would actually have to do some math here. But this is kind of just a quick way if you need to quickly answer a question. All right, you're mixing two salt solutions that have a common ion. The salt that has the lower KSP will precipitate first as long as they have the same number of ions in each. Now we're going to look at how pressure impacts an equilibrium system here. So the way we kind of change pressure is by messing with the volume. So if we drop the volume of a system, essentially we lower the amount of space it can take place in, that will increase the pressure. If you have less overall space for the same amount of stuff, you're going to increase the pressure here of the system, and vice versa. If you have a system and you increase the amount of space it's taking place in, the pressure will be lowered. So that's important. You need to understand here that messing with the volume impacts the pressure. Okay, so if you increase the pressure in a system, Le Chatelier's principle says, well, you need to minimize that stress. You need to figure out a way here to lessen the pressure. If you made the pressure go up, the equilibrium is going to respond by trying to decrease that pressure. Well, the way the equilibrium can do this is by shifting here to the side that has less molecules of gas. Okay, so as long as you're not changing the temperature, if you drop the volume, that will increase the pressure on the system. So the equilibrium will shift to the side with fewer molecules of gas because that will lower the overall pressure. Essentially, more molecules of gas are going to be used up in the reaction to form less molecules of gas, so the overall pressure will lower. You really need to think about this one, okay? Decreasing the volume makes the pressure go up, so the equilibrium is going to shift in a way that decreases the pressure. And the way the pressure decreases is by shifting to the side that has fewer molecules of gas. Be careful here. It's specifically fewer molecules of gas because that would create less pressure here. So this definitely requires some thought. Let's look at an example here. We have the same reaction that we used previously. N2 plus H2 is going to NH3 here. So if we increase the pressure, all right, we decrease the volume here that this is taking place, which increases the pressure on this system, okay? The reaction, the equilibrium will shift in a way to minimize that increase in pressure. Essentially, it wants to shift to the side with less molecules of gas. So if we look at this, the N2 and the H2 are both gas. So on the left side, there are 4 molecules of gas. 1 N2, 3 H2, 4 molecules of gas. On the right side, there's only 2 molecules of gas. So if I increase the pressure on this system, it's going to shift to the side with less gas. It's going to shift to the right or to the product side, okay? Essentially, it's going to use up more molecules of gas to form less molecules of gas, which would lower the pressure here. All right, you really need to think about this, but the system is going to respond in a way to decrease the pressure here. It's going to decrease essentially the stress you applied on the system. So if you increase the pressure, it's going to shift to the side with less molecules of gas in order to decrease the pressure that you put on the system here. Now we want to look at this same idea in picture form here. It's very important to understand this on a molecular level for AP. So it's the same reaction. You can see the key over here, the N2 and the H2, what they look like, and then the NH3 here. So if we increase the pressure on this system by decreasing the volume, all right, if we increase the pressure, we said it's going to shift to the side with fewer molecules of gas, which we said it should shift to the product side. So essentially, we should see more NH3 forming here. So when we increase the pressure by decreasing the volume, there's more pressure. If you notice in the picture here, we have more of the NH3 forming here in this last picture. All right, very important. We're able to see that we did shift the reaction and it shifted to the side with fewer molecules of gas, in this case, the products. All right, so you would need to be able to possibly interpret this and explain this also on a molecular level as well. We also need to consider how temperature changes will affect a system at equilibrium. Okay, so the effects here of the temperature change are going to depend on whether or not the reaction itself is endothermic or exothermic. You need to think of each type here as a reaction with heat as a reactant or product. So for example, if you have an endothermic reaction, in your head you should be saying, okay, energy is going to enter. All right, so it's going to feel colder. So essentially what's happening is you have the reactants plus heat here forming your products. Essentially, heat is part of your reactants. Is it going into your reaction? It's being used up, if you will. But if you have an exothermic reaction, heat is exiting, so you need heat to be one of your products. So your reactants is going to the products plus heat. This is the only way heat could exit the reaction is if it's formed. All right, so that's the easiest way to think about this. In an endothermic reaction, heat is being used up, so it's part of the reactants, but in an exothermic reaction, it is exiting or leaving, so it needs to be one of the products here. We need to look at each of these kind of separately here. All right, we already know that an endothermic reaction would have heat as one of the reactants, essentially. You're absorbing heat or you're using heat up in a endothermic reaction. So if you increase the temperature here on an endothermic reaction, all right, think about this. You have a system at equilibrium. It's an endothermic reaction. If you make it hotter, it needs to shift in a way to use up the added heat. All right, you increase the temperature, it needs to use up that heat. The only way it can use up that heat is by going to the right. All right, since heat is a reactant, it's going to get used up by forming more of the products here. Basically, it removes the added heat in your equilibrium. And then if you were to decrease the temperature of an endothermic reaction, think about this. You make the reaction colder. Essentially, the reaction is saying, okay, it's too cold. I need to form more heat. Well, the way it's going to form more heat or add more heat is by going to the left. Essentially, you're going to form the reactants here because heat is one of the reactants here. So it would shift to the left. All right, you really need to think about this and fully understand what happens here in an endothermic if you increase or decrease the temp. I told you this is a lot of thinking here. In an exothermic reaction, we said that heat is a product. So if you increase the temperature on an exothermic reaction, it is going to be too warm, so it needs to shift in the direction that removes the heat. So if you have an exothermic reaction and you increase the temp, it's going to go to the left to use up the heat because the heat is a product here. All right. And if you decrease the temp of an exothermic reaction, imagine it's saying, okay, I'm cold, I need to form more heat. Well, by going forward or going to the right, forming the products, that's how you generate more heat in an exothermic reaction. So you really need to think about each of these separately and make sure you understand what's happening for each if you increase or decrease the temperature. You need to know which way they're going to shift in response to that stress. You need to be able to look at graphs like this and understand what's happening. So if you look at this first one on the left, it says we have CO2 plus energy forming CO and O2. So obviously, if energy is a reactant, that's going to make this an endothermic reaction here. Essentially, you could actually figure that out by looking at this graph. So notice here, it's telling you that the temperature is decreased here. All right. So when the temperature drops at this point, notice what's happening. Notice what's happening. All right. The amount of the CO2 is going up, and then the amount of the CO is going down. All right. And the amount of the O2 also goes down. All right. So if we make it colder, all right, we can see here that the reaction needs to shift in a way to generate more energy or generate more heat. So we would know it's going to shift to the left here, and we can prove that from this graph. We're forming more of the CO2, we're forming more of the reactants, and we're using up the products, so they're decreasing. Again, you didn't have to be told that the energy was a reactant here, or even that this was endo. If all I gave you was this reaction without the energy in it, and you see here that the temperature drops, and the reactants are going up and the products are going down, you would realize, well, as it got colder, it's going to need to generate energy, all right, or add energy here. So if it shifts to the left, that's telling you it's generating energy when you go left. So that must mean energy is part of the reactants. Therefore, this is endothermic. Okay, so you need to be able to really think about this. If you look at the one here on the right, this is showing you that this is an exothermic reaction. Energy is a product. When we drop the temperature at this point, if you look at what happens here, the SO2 is going down, and the O2 is going down, but the SO3 is going up. So essentially, we're forming more of the products here. If we make this colder, the system's going to respond by needing to generate more heat, more energy. So it's shifting to the product side here because this is exothermic. You're going to generate more heat, and that's what we see happening. The products are forming and the reactants are used up. Again, without even knowing that this is exo, you could figure that out as well. If all you knew was the reaction without the energy in it, if you decrease the temperature at this point and you see that the reactants are used up and the products are forming, that would tell you when you made it colder, it's going to the products to generate the energy. Therefore, the energy must be on the product side, and this must be exothermic. So you really need to understand what's going on here when you change the temperature, especially when it's exo or endo. Catalysts have no effect on the equilibrium, all right? So they're not going to be a stressor here. Essentially, they speed up the forward and the reverse reaction exactly the same. So basically, they increase the rate at which you get to equilibrium, but it's not changing the actual composition here of the equilibrium mixture. They just basically allow you to get there faster, but your equilibrium mixture essentially has the exact same composition here. So if you look at this kind of in picture form, you can see the difference here between the catalyzed and the uncatalyzed reaction. The catalyzed reaction is in red, and the uncatalyzed reaction here is in black. If you notice, you reach that equilibrium position a little bit faster for the red or for the catalyzed reaction, but essentially they both end up at the exact same spot. So catalysts have no effect on equilibrium. Don't fall for any tricks here. How is KEQ affected by these stressors? Well, if you change the concentration or you change the volume leading to a pressure change here, they have no effect on the value of KEQ. All right, so concentration, pressure, volume, no effect on KEQ. But if you remember from earlier in equilibrium, if you change the temperature, you change the value here of the KEQ. All right, so you need to see what's actually happening here when you change the temperature. All right, so it depends on, whether you're increasing or decreasing the temperature and whether it's exo or endo. But the basic gist is if you shift the reaction to the left, all right, whether it's exo or endo, if you're going to the left, you're going to have a decrease in your KEQ. And this makes sense. As you go to the left, you're forming reactants, and KEQ is products over reactants. So if you have more reactants, essentially, your KEQ is going to be lower. All right, so just think about this in terms of what KEQ means. And if you have a shift to the right here, again, whether it's exo or endo, if you are going to the right, you're forming more products. KEQ is products over reactants. Now you have more of your top number. Your KEQ is going to be greater. All right, so you really need to think about this and make sure you understand this. If you change the temperature, that will impact the value of KEQ, and depending on which way you shift, that will determine whether KEQ increases or decreases. Catalysts or other compounds that are not present in the reaction have no effect on the KEQ or the equilibrium itself. So don't fall for any tricks here as well. Sometimes you might add something to the equilibrium that has no effect on, the equilibrium. It's not a catalyst, maybe. It's not in the actual equilibrium. It's kind of just a trick. They have no effect on KEQ itself or equilibrium. So the temperature here, you change the temperature, you're going to change the value of KEQ. The other things like concentration, pressure, volume, catalyst, no effect on KEQ. Let's look at an example here. This is how you might need to think about this, and you really need to be good with your explanations as well. AP will make you explain your answers here. So this says, consider the equilibrium reaction below. In which direction will the equilibrium shift when you do or apply these different stressors here? So what I would do right now is I would pause the video, look at A through E, and determine which way the equilibrium is going to shift. Is it going to go left or right? Is it going to go to the reactants or the products? And then rejoin the video and see how you did here and walk through the explanation with me. So I would pause the video right now and try this. All right, so now I'm going to walk through these answers here. So the first one, A, says N2O4 is added to the equilibrium. So you have more here of a reactant. So the equilibrium needs to shift to use up this added reactant. So it's going to go to the product side. All right, so for A, you're going to go to the right here, and you're going to form products. All right, let's look at B. B says NO2 is removed. So essentially, as you form this NO2 gas, it's being removed from the system, so there's less of it. Well, the equilibrium is going to shift in a way to form more of that. So again, we are also going to go to the right here as well. When we look at C, C here says the total pressure is increased by the addition of N2 gas. So we're increasing the pressure here. So if we have more pressure, we have to look at the number of molecules of gas here. So if we look on the left side, we only have one molecule of gas, just N2O4. On the right side, we have two molecules of gas. So now if we have the pressure increasing, we need to shift the reaction in a way that decreases the pressure. So we're going to shift to the side with less molecules of gas here. So the side with less molecules of gas would be the side with one. So we're going to go to the left. All right. So now when we do D, D says the volume is increased. All right. So if you increase the amount of space the reaction is taking place in, that doesn't necessarily affect it, but it's going to change the pressure here. All right. So if you increase the volume, you're going to decrease the pressure. So if you decrease or lower the pressure, you need to shift to the side of the reaction that has more moles of gas, essentially to increase that pressure. So we're going to go to the right here, the side with two molecules of gas. And then we have E. E says the temperature is decreased. So the first thing you need to realize is here, we're given delta H information here. All right. Delta H is your change in energy. If you have a positive value for your delta H, that means that this is an endothermic reaction here. Essentially, energy is entering this reaction. Energy is being absorbed, so it's an endothermic reaction. If you have a negative delta H, that's when you have an exothermic reaction. Energy is exiting. So very important that you can look at this delta H and know that a positive value means it's endothermic and a negative value means it's exothermic or energy is exiting. So this is telling us this reaction is endothermic. So if I decrease the temperature here, okay, so if I drop the temperature, make it colder, I need to shift in the direction that generates more heat. All right. If this is endothermic, the heat is a reactant. So making it colder means I need to shift to the side that has the heat or shift to the reactant side to generate the heat here. So this is going to go to the left. All right. Very important that you can use the delta H information to be able to figure out which way the reaction will shift if you change the temperature. We have another example here. Again, we're given an equilibrium reaction, and we want to know which way the equilibrium will shift when we apply these different stressors. So I would pause the video right now, try this on your own, and when you rejoin, I'll have all the answers there, and you can see how you did here. So I would pause the video right now. Okay, so hopefully you got these answers. For A here, when chlorine gas is removed, so as we remove this product as it is formed, all right, we need to shift to the right or to the product side to generate more of that chlorine gas. For B, if we increase the temperature, again, this is a positive delta H, all right, so that tells us the reaction is endothermic, so it's going to absorb heat. Heat is going to be a reactant, so if we increase the temperature, essentially we need to use up heat here. We got too warm, so we need to use up the heat. Well, heat's a reactant, so it's going to go to the right to use up that heat. It's going to form more product here. For C, the volume of the reaction system is decreased. So when you decrease the volume, you increase the pressure here. So we need to shift to the side with less molecules of gas to decrease the pressure. We have one molecule of gas on the left, two molecules of gas on the right. So we're going to shift to the left side with less molecules of gas. And then for D, it says that we're adding PCl3 gas here. PCl3 is a product. So if there's more product, it's going to shift to the side to use up that product. Essentially, it's going to shift to the left here. So you definitely need to be able to understand what happens and be able to explain these stressors, all right, which way the reaction is going to shift, giving good explanations here. So I said there's not a lot of math here with Le Chatelier's. So I wanted to just give you an equilibrium problem that kind of uses information from different areas here of the course. All right, typically AP combines information from different units. So I just wanted you to see kind of a problem here. We have to think about the problem a little differently using equilibrium information, but also information from other units. So you can see it's kind of long here. But they're basically telling you at temperatures of 800 degrees Celsius, steam is passed over hot coke, which is a form of carbon from coal, and it reacts to form CO and H2 as you see below here. All right, so then it goes through different questions here. So we'll go through each of these kind of one at a time, give you a chance kind of to try these and then see how you do. Part A says at 800 degrees Celsius, the Kp for this reaction is 14.1. What are the equilibrium partial pressures for H2O, CO, and H2 if we start with solid carbon and 0.100 moles of water in a 1 liter vessel? Okay, so we are trying to find the equilibrium partial pressures of all of these substances. So we don't know any of the concentrations at equilibrium. So we know we're going to need to use an ice table with X here, but we're not quite there yet. Okay, so what I would do is I would pause the video right now, see what you come up with. When you rejoin this, I'll have the full answer here and then I'll walk you through this. But I want you to think about this first on your own and see what you come up with. So pause the video right now and try part A. Okay, so this is how you would actually solve this problem. If you notice here, they're asking about the equilibrium partial pressures, but what we're given is the moles of water in a 1 liter vessel. Essentially, we're in concentration, but we need pressure. So we have to actually use PV equals nRT first, all right? So this problem is using actually a gas law, and then it's going to use equilibrium to be able to solve the problem here. So we plug in all the information we know about water into PV equals nRT, and that will allow us to solve here for the pressure of the water. Essentially, we have the moles, we have the liters. We don't have the pressure of the water. Now that we have the pressure of the water using PV equals nRT, now we can plug into our ice table, all right? The carbon is a solid, so it doesn't participate in your equilibrium. You know now the pressure of the water. You know the initial pressures here of the CO and the H2 are 0, so we know the reaction is going to form products. They're going to be positive, and the reactants are going to be used up, so that's going to be negative. So now we have our equilibrium values here for the pressure. So we write our Kp expression. Again, no solids in your Kp expression. Plug in what we know, solve for x. You do have to use the quadratic here. You do get two answers. X being 6.13 ATMs is the only meaningful answer. So now you go back to your equilibrium here, plug in the value of x, and you find the pressure of water being 2.67 ATM and the pressure of CO and H2 both being the 6.13 ATM. So I just wanted you to see here how sometimes you might have to combine information from different units here. And this is really thinking kind of at a higher level here. I needed to take information about gas laws and information from equilibrium and kind of put them together to solve part A. Now for part B, we want to know the minimum amount of carbon required to achieve this equilibrium. All right, so I want you to think about this. You're going to have to use information from the previous part in order to see what you need here, all right, to get the minimum amount of carbon required to get to equilibrium. So again, I would pause the video right now, see what you can do, and then rejoin and see the solution. So pause the video and try it on your own right now. Okay, so here's the answer for this one. So from the previous part, we knew that we used up 6.13 ATMs of water in the problem. Uh, Remember here, that's your reactant that we care about. So that's the one that we need to focus on here. That was essentially what was being used up. If you remember, we were subtracting 6.13 ATMs here. So that much water is used up, but that's in pressure, okay? In order to figure out how much carbon we need to react with that, we need to know the moles of water that is. So again, it's going to be a PV equals nRT. We know the pressure of the water that was used up. We know the volume that we were in. We know R. We know the temperature. We find the number of moles of water that we used, right? That's the amount of pressure that was used up. Well, that's the equivalent to that many moles of water that we used. So now if we're trying to figure out the amount of carbon, if you use that many moles of water, there's 1 mole of water for every 1 mole of carbon. All right, we know there's 12.01 grams of carbon for every 1 mole. So obviously you must have had 0.837 grams of carbon in order to use up that many moles of water. So you can see here how we had to use kind of PV equals nRT, information from gases, and also do some stoich here in order to figure this one out. So we're kind of combining information here from different units. Part C says, what is the total pressure in the vessel at equilibrium? So you can pause this and see how you do on your own and then come back. I'm just going to continue solving this. So if you want to pause it, do it now. Otherwise, I'm going to walk you through this. So remember, in part A, we found the 3 pressures here of the gases at equilibrium. So we have those values. You just need to add them up. We said that 2 of them are at 6.13 ATMs. Okay, and the other one was at 2.67 ATMs. So the total pressure of all the gases here at equilibrium is just those partial pressures added up. That's going to be Dalton's law here. So when we total this up, it's just 14.93 ATMs. All we had to do was add the individual partial pressure of the gases at equilibrium from part A. Part D says at 25 degrees Celsius, the value of Kp for this reaction is 1.7 times 10 to the negative 21st. Is the reaction exothermic or endothermic here? Remember, our original Kp was 14.1 at 800 degrees Celsius. So that's going to be important here. All right. So notice when we drop the temperature, all right, if we drop the temperature here, we're going to 25 degrees Celsius, from 800 to 25 degrees Celsius. What happened here to our Kp? As we dropped the temperature, the Kp also decreased. It got much lower here as the temperature lowered. All right. So essentially what that means is if the Kp is lower, all right, Kp is products over reactants, you have more reactants present when we lower the temperature here. All right. So if you have more reactants present when you made it colder, All right, think about this. If you make it colder, the reaction needs to shift in a way to generate more heat. So if there's more reactants present now because you have a lower Kp, that means the reaction shifted to the reactants to generate more heat. So if it's shifting to the reactants to generate more heat here, that must mean heat is a reactant. Therefore, this reaction is going to be endothermic. Okay, essentially it's shifting to the side with the heat, and the heat is a reactant here. So that must make this endothermic. You really need to think about this. If you decrease the temperature, you make it colder, the Kp decreases, which means you have more of the reactants forming. All right, more reactants here as you made it colder means it's shifting to the side that has the heat. All right, it's responding to the stress. Well, that means heat is a reactant, so it's going to be endothermic. You have an endothermic reaction when heat is a reactant. This is very important to understand this, be able to do something like this. This is a pretty common question, being able to understand how the Kp changing when the temperature changes, what that means for endo or exothermic. And finally here for part E, it says to produce the maximum amount of CO and H2 at equilibrium, should the pressure of the system be increased or decreased? All right, we want to form the maximum amount of these two. All right, so if you notice here on the right side where they're at, there's 2 moles of gas, okay, 2 gas molecules here. On the left side, there's just 1 molecule of gas here with the water. All right, remember, this is a solid. It doesn't participate here. So we have 2 to 1. All right, so if we want to form more of the CO and the H2, all right, you got to think about what should we do to the pressure here. All right, if you decrease the pressure, all right, it's going to shift to the side with more molecules of gas here. It's going to shift to the side with more molecules of gas to increase that pressure. So by decreasing the pressure, we would shift to the CO and the H2 side because they have more molecules of gas on that side. Therefore, that would form more CO and H2. So this is kind of using this information about pressure and Le Chatelier's to be able to think about, okay, how could I generate more of the products in this case? All right, so decreasing the pressure means you need to shift to the side with more molecules of gas, which would be the right side, which would generate more CO and H2.